There you go. All right. So if we take a look down here, I think you guys are probably overfed with conjugate acid, conjugate base thing. We'll do one of these. Whenever you look at this, NH4 is becoming NH3. It is losing a proton. A proton is a fancy word for hydrogen ion, because remember, a hydrogen atom is a proton with one electron, right? A hydrogen ion has lost that electron, so they just call it the proton. What's left is the nucleus. So that is an acid, and it forms the conjugate base. Here we have H3O accepting that proton. That is its conjugate acid. The fact that, did I do it? They didn't. The fact that H2O can become H3O or H2O can become OH negative makes H2O what's called an amphoteric substance. That means it can be an acid or a base. It's not the only amphoteric substance. There are others out there. Here we go. Nope, they still have H2O acting. Let's look at this. Here we have a CO3 2 negative. It is accepting. So this is the conjugate acid of it. Since it has this negative right here, that means it could do what again? This HCO3 negative could also, instead of becoming a conjugate acid, right, and acting as an acid, it could also accept again, because it still has that negative. Means it could accept another hydrogen and act as a base. It is still called the conjugate acid of this base in this reaction. There, yeah. So in the first set, H2O is acting as a base. In the second set, H2O is acting as an acid to get you that idea of that amphoteric substance, H2O. So you try. In the following reaction, identify the acid on the left and its conjugate base on the right. So which of these substances is acting as an acid, HBr or NH3? Great. Put a little A there. And that makes this Br negative, its conjugate base. And it's funny, that's all it asks. Oh, no, then it says similarly identify the base. So then we would know this is the base, this is the conjugate acid. What is the conjugate base of H2S? So they're telling us H2S is acting as an acid. Close. We've lost the positive, so we've become negative, right? And what is the conjugate acid of NO3 negative? HNO3. So hopefully you won't miss any of those questions. Trying to think, there was a statistic of the amount of acid-base questions on the AP test is kind of high. Basically because you could talk about acid base and get so many other things out of the way as well, right? So acids donate only one proton at a time. If it only has one, we would say it's monoprotic. Mono means one, di means two. Diprotic like H2C2O4 or oxalic acid, sulfuric acid, carbonic acid. Polyprotic just means it has many H's. You could also call this triprotic, H3PO4, because it has three. Mono covers a huge amount. There are bases with more than one, for example, calcium hydroxide and aluminum hydroxide. Those would have, those would be able to accept more H's. You also have these guys too, which would be the conjugate base of HPO4 2 negative. And you can see that as we take away H's from this, then if we have these guys, we can accept them back. And there's that word, Amphoteric. So you have that there. Let's do a few of these and I'll let you finish them up. I'll just cover up your answers down here. So write the simple dissociation reaction for each of the following acids. HCl plus H2O is going to yield H3O plus, the hydronium ion, plus Cl negative. Well, what if it asks us for the net ion reaction here? This one gets kind of weird because it's going to be the same for all the strong acids. We did the net ionic here. I'm going to just do it right up here. We get H plus Cl negative plus H2O liquid yields H3O plus Cl negative. What's going to cancel out? What's the same on both sides? It doesn't take part in anything. Spectator ion, good. And in this case, it is the Cl negative. So we would get H plus H2O yields H3O plus. Right? That's not the same when you have something like acetic acid. Can anybody tell me why acetic acid, we would not have that same thing? Doesn't properly dissociate. Well, not properly might not be the right term for it, but yeah, HC2H3O2 plus H2O is going to yield H3O plus C2H3O2 negative. So since this does not completely ionize, we actually hold that together. Yeah, there's only 6 strong acids. Was there a list in here somewhere? I'm sure it's coming up if it wasn't there. So those are the basics for that. And I believe it mentions this somewhere in here too, that it's been accepted that you don't need to put H2O in there. That's why they have H plus down here and they don't have the H2O right here. It is the same thing in most people's mind at this point. That's why you see most of the time whenever we're writing the hydrogen ion concentration instead of the hydronium, just quicker. But H3O plus is exactly the same as H plus. If you give a question or anything, please let me know by all means. Again, I'm considering a lot of this to be review for you. So if we take a look, here we come with relative strengths of acids and bases. Now keep in mind that when we talk about strengths of acids and bases, we're not yeah, there it is right there. We're not talking about concentration. So keep that in mind. The strength refers to the dissociation constant for them. So if we take a look, you have HA at equilibrium in a strong acid, strong base, all of it separates. And this is just talking acids here, but it's going to be the same for bases. With weak, only a very small percentage actually dissociate. Here are the strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. If we take a look, remember that hydrogen is quite a small, that proton is quite a small particle, right? And if we take a look at the bond strength here for the hydrogen fluoride bond, it's quite high. versus for the HI bond. Hence, hydroiodic acid is a strong one because it's all about the ability to remove that hydrogen off. If it can remove that hydrogen off, or that hydrogen can be pulled off easily, then it's going to be stronger. If it doesn't dissociate, like this one, it's not going to happen. Now, whenever we're talking about this within a polyatomic ion, notice that perchlorate, right? Perchlorate has a lot more oxygens on it. What that's going to do to the electron dense, the high electron density areas, that's going to pull these electrons towards this way. Well, if we pull those electrons towards this way, then we can see that these will be pulled away from the hydrogen in a sense. Well, if they're pulled away from the hydrogen, what is a hydrogen without any electrons? It's a proton, right? That H plus. So the more oxygens you have on there, the stronger it's going to be. And they do have the Ka values for some of these. You can see for perchloric, it's strong. So it's going to ionize completely. For sulfuric, it's large enough, it ionizes completely. For the other ones, the chlorate, the chlorite and hypochlorite, it decreases quite a bit. Same thing with nitric, ionizes completely. And then for the nitrous, we don't see that happening. Does that make sense? If we take a look for a carboxylic acid, same thing. We have this oxygen here, which is going to basically act as that high electron dense area. That these electrons here are going to get pulled into here, and the hydrogen is going to be able to be attacked. Hold on. Strong bases. So alkaline earth metals, except for magnesium and beryllium, they are going to be strong bases whenever they're with hydroxide. And that's it. So if we take a look here, with these strong bases, again, these aren't the KAs for those, but here we go. Okay. So when we talk about these strong bases, keep in mind that if they're not readily soluble, then they're not going to be strong. It also deals with the solubility product constant. And let's say you have HCl, and that goes to H plus Cl minus, right? So this Cl minus would be conjugate base. Since this is a very strong acid, this conjugate base will be very weak, which makes sense if we try to get this to pair up with an H, right? Or to try to get an H, but we know that it's going to lose it quite quickly, right? Because it forms HCl and HCl dissociates almost completely, right? So that makes that a very weak base or proton acceptor. If we have a weak base, like NH4, I'm sorry, a weak acid like NH4 plus, and that gives a stronger base. Or if we have, we can use, I think this is fine. So a weak acid like NH4 plus gives a stronger base, NH3. Now this isn't a strong base, but it's one of the stronger ones. One of the stronger ones. Weak acids, weak bases, they are based on that that Ka or that equilibrium constant for the acid. Dissociation basically just means the separating of each other. Dissociating this H is what it refers to for an acid. Creating the OH or dissociating an OH off is what it would be for the base most of the time. So if we take a look here, this is their denoted acid. That acid is attached to an H. If we put it in water, it loses that H, and then the anion goes off by itself. Keep in mind that this A negative is the conjugate base. It's one of those things. I mean, this is trying to stand for, the A is trying to stand for acid. It's not anion or anything like that. It's just using like a shorthand to sit and say, okay, with the H, this acid has the H, and without the H, it's no longer acid, it's conjugate base. As always, products over reactants. H2O is not in there because H2O is a liquid, so it would count as 1. The greater this is, the more the acid dissociates, the stronger the acid. And keep in mind, when I say the stronger the acid, that doesn't mean it's necessarily a strong acid. There's only 6 of them.
Mr. Jackson, I don't know if it is the same for other people, but when you turn around to talk to the class, I like can't hear
Can't
you.
hear me anymore? All right. How about now? Just sit like this and do the rest of it. All right, let's take a look then. Here is our table. Hopefully you guys can see this. If not, you can pull it up and pull it and get it from that thing, from the file. But these are the relative Kas for common monoprotic acids. Now, again, whenever you're looking at these, the smaller this is, this -2 versus -10, the closer to 1 it is, which means that it will be stronger. We know that all of these weak acids are going to have a Ka or an equilibrium constant less than 1, but the closer they are to 1, the stronger they are. So if we take a look, here is acetic acid, HC2H3O2 plus H2O yields H3O plus C2H3O2 minus. So to write the Ka expression, we will put the products on top. And the reactants on bottom. We're not including water here. So if we were to want to solve for this, right? Basically, we have the concentration of the acid, which would be this that we're starting with. And it will dissociate to give you some type of ratio. Well, the amount of this that is created is equal to the amount of this. So basically, if we call both of those X, right? Whatever this concentration is down here will be whatever it was starting minus X, but that will be very small. And this all will be equal to the Ka. So an easy way to look at this is, since X, right? If this is X and this is X, that's X squared. So the hydrogen ion concentration is equal to that X. If we take the Ka and multiply it by the molarity of the acid, and then we square root both sides, That will give us the hydrogen ion concentration for these weak acids. That is a quick way to do it. Here's the thing I wrote out earlier for ammonia. We can see that we have these 2 electrons here, and it's going to cause these electrons to basically go back, and then these will attack, and we will get the NH4, and that's how ammonia produces the OH. Nitrogen is awesome at that. You can see all of these lone pairs of electrons there. That's going to allow them to act as bases, electron donors. KB stuff is exactly the same. You get the OH concentration. So if you have OH is equal to the square root of Ka times the molarity of the base, and the square root of that. And I'm sorry, not Ka, Kb times the molarity of the base. That will be the OH concentration. Keep in mind, then I can find the POH by taking the negative log of that. This is one that kind of tricks the students up sometimes, because something will ask for the pH, and they'll sit there and they will find the POH, but they won't go that extra step. How would I find the pH after this? Not everybody at once. 14 minus that POH, right? So if you find the hydroxide ion concentration, you can find the POH by taking the negative log of that and then subtracting it from 14 to get the pH from the POH. Write the Kb expression for ammonia. So if we take a look, ammonia plus water yields NH4 plus OH negative. Again, products, overreactants, and again, this will be the concentration of the, dang it, let me do some out or something. This will be the concentration of that base. We also would have that minus X there. If we had this X, and this would be the concentration of the base minus that X. And that's going to allow you to do that same thing up here. And that B up here looks terrible, so I'm going to change it to a good looking B. Cool. Now here's that thing. It says, while the acid produces hydrogen, hydrogen ion or hydronium ion, bases produce the hydroxide ion. So that's a key thing that you're going to want to take a look at. That's that finding the OH concentration versus finding the H positive concentration. And here it says often water is left out of the equation. So down here it says using table 14.2. This is 14.2. If these are the acids, then arrange these species according to their strengths as bases. So you know that the stronger the acid, the weaker the conjugate base, and the weaker the acid, the stronger conjugate base. So you should be able to check those out and figure those out. And I think I'm done for today. I think that's good. Tomorrow we'll go over the KW stuff and let you guys use that 4-corner diagram again. So tonight, make sure you understand this part right here. Make sure you can figure out how to use that table, use those strengths to work through. All right. Questions?